Here's a red SparkFun ATEC 508A cryptographic coprocessor breakup board connected to an Arduino while using a 3.3-volt power supply from Ockam RX. A lot of network protocols have their own security. What Ockam does is decouple the secure transport protocol from the transport protocol and provide its own end-to-end encrypted secure channel. Here's a configuration file from Ockam. When I started, I did not know what I was doing. I burned the configuration to the chip, and I was surprised when it did not work as I expected it to. I see it has 3 slots for the ECDH master secret. This led me to think about extended triple Diffie-Hellman. However, they mentioned the noise framework. Ockam is trying to implement a protocol using this, and they are working to use curve 25519 instead of P256 used here. I modified SparkFun example 1 to write the configuration from config ATEC 508.py. I did not lock any zone on the chip. I just uncommented zones of my code and did writes. I then broke up the rest of example 1. The big change was targeting the slot when creating each key pair. I believe I may have locked each data slot individually instead of all at once. You could see my configuration matches the Python example. After looking at the underlying datasheet, I believe that running the SparkFun example is functionally equivalent to running the Python code. Why? I hit the same opcodes and I had the same hex arguments to it, as it seemed. Example 2 in the SparkFun tutorial involves creating a cryptographic signature with a private key. I modified the example in an attempt to target the multiple keys that I created using the configuration in ATEC 508A.py. Unfortunately, I was not successful with creating a signature. I can hook the cryptographic authentication chip to the Heltec Cube cell. Occasionally I will get an error that tells me it cannot find the device even though I hooked it up correctly. In this case I use an I2C scanner. Modifying ATEC 508A address default in SparkFun ATEC X08A Arduino library.h with this value fixed my problem. In my case I created a copy of the library and loaded this modification into an Arduino environment. Unfortunately I found that the Heltec Cube cell was unable to display the public key even though I generated it successfully previously. I found that I could successfully view the public key with the SparkFun printinfo function in example 1 for both your Arduino Uno chip and a ESP32. Comparing the hardware specifications tells me the Cube cell should work with the CryptoChip. Example 1 utilizes a wire library. I compare the Cube cell's wire library with that of the Heltec ESP32 and the Arduino Uno. I suspect that the I2C connection in the Cube cell wire library is set to timeout too soon. I did get the first 2 examples from the SparkFun library to run. This allowed me to create a public key and create a signature. I have a 64-byte uncompressed public key consisting of X and Y P256 elliptic curve coordinates. I have a 32-byte message, and I have a 64-byte signature of the message created by signing with the private key corresponding to the public key. I wrote code that converted a byte array in hex to an array containing specified equal length hex strings, and then I hard-coded converting these hex strings into type int. The public key was represented as 2 32-byte hex strings as XY coordinates. I was able to grab these hex strings from the previous code. The signature was entered as a pair of 32-byte hex strings RS. Message hash is the integer form the hex array for the message. Failure 1 is I cannot get the public key from the CryptoChip. Supposedly this is due to the wire library and the Heltec Cube cell, so I need to investigate that. Failure 2 is I can get the public keys on the chip configured with config ATEC 508.py from Ockam, but I'm unable to proceed to example 2 and get the signature. What are the benefits of decentralized public key infrastructure? DPKI versus PKI public key infrastructure. DPKI provides a way to move device identity to the edge rather than a centralized architecture. Proving identity is through the private key. DPKI is a decentralized architecture which is harder to compromise. With PKI, one certificate authority can be compromised leading to spoofing. With DPKI, many must. More to the details than a permission ledger, the quote-unquote certificate authority seems to be the verifier with an associated governance framework. DPKI, with the DID specs, provides a strong decentralized authentication scheme. A lot of ledgers in the decentralized identity or DID space seem to prefer the ED 25519 curve. One ledger, the sovereign ledger, supports the NIST P256 curve. Maybe all ledgers do? I'm not sure how this will work. I guess I could embed the P256 key in a DID document signed by the ED 25519 key, or if it's possible, have a DID document for the P256 key, or a combination of the two. Another place to plug in is BigChainDB. With BigChainDB, I may not have to think about an external place to store my data in addition to the small amount of data used for trust on the ledger, like IPFS.